Hey, my name is Edward Baker, and I'm a senior in COMP572. This is my final project on creating HDR images. So here's the problem statement. The goal is to take a set of LDR images or low dynamic range images and convert them to HDR, high dynamic range. So HDR photography, if you recall from class, is the method of capturing photographs containing a greater dynamic range than what normal photographs can contain. This improves the overall picture quality by introducing brighter highlights and a wider range of colors compared to SDR photos. Why does this matter? Because the real world is high dynamic range, and the more realistic or the more dynamic range a photo can contain, the more realistic it is. So how can we create HDR images? Well, one method to do this is by combining multiple LDR images at varying exposures. So that's what this project explores. And the methods we use to do this, using the original HDR image series for the Stanford Memorial Church radiance map from the paper by Dibivek and Malik on recovering high dynamic range. The naive methods were attempted first, then the advanced, and the advanced methods follow the work outlined by Dibivek and Malik, and I actually used some of their code as suggested in the write-up. So the naive approach, first, I'll just give a really brief technical overview of what we did here. The simple average is basically normalizing the exposure values in the LDR photos and then just taking an average of all of them. The weighted average is applying a weight of either 0 or 1 to remove some underexposed or overexposed values. And the under and overexposed values getting the weight of 0 to be removed. The median weighted average is using a little bit more of an intelligent metric. So the weights are going to be max in the middle of a range and then taper off for higher values. And then the median values is removing those under or overexposed values and choosing the median. And then the highest non-saturating exposure is going to be choosing a pixel that's the maximum of less than 80% value of 255. So those are the naive methods. You can see decent results, but not great. And then the advanced method here is the function to recover the high dynamic range radiance map. And so what we're doing here is we have the response curve G, and we have the code from that from the paper. And so once the response curve G is recovered for each color channel, we can convert pixel values to the relative radiance values, assuming the exposure delta TJ is known, which it is for us. And then all we do is apply the weighting function as well. And to recover the HDR radiance values, we're going to use all the available exposures for a particular pixel to compute its radiance. We exponentiate this result, and here we get this. And so as you can see on the left, there's our result, and on the right is our response function plotted for each color channel. And I realized that there's an issue with the blue borders here. It's creating a lot of noise and skewing the results. And as you can see, even the advanced method produces something that's really suboptimal. It still has those artifacts in the top left and bottom. So I solved this by identifying the pictures with the largest blue borders, cropping those images down to remove the borders, and then applying that crop to all the images. Here's the naive approach post-crop. As you can see, much better results, less grainy, more details in the shadows. There's the advanced method, a lot sharper photo overall. And if you'll notice on the right, the response function, that blue has a lot less variance towards the top of the graph. And then here we can see a direct comparison between the two, just to highlight the differences and how helpful that crop really was. And then the advanced method as well. So you can see a much sharper image, less washed out, more brighter brights, better shadows, and a better approach. And then finally, here's another look at the response function graphs just to highlight the change that crop made. So that's my final project. Thank you for watching.